Number 6, 1/4. Number 20. Did you guys use the ln property? Final answer 2. Yeah.
Wait. It's not ln too? No, it is ln too.
Oh, we didn't keep going. Sorry. I wasn't paying attention. 2 was one side, or was the inside, and then ln's on the outside, so we need to go
Can
and
you
do
think of it like as like the coefficient thing? So it's like 20 times or like.
Well, you can think of it as you can bring the limit into the composition. You can take the limit of the inside. It was a property that we looked at last year. I don't think we wrote down. That the limit of f of g is the same thing as f of the limit of g. I think that sounds right. And so you can bring the limit in. You can take the limit to infinity of the argument, which would be 2, and then ln of 2. Well, I mean, I guess you can just take the limit as is and just plug in. ln of 2 is the final answer. See, there's a niveau because it is a determinant, but you could just do degree tests, which I think is what you were talking about. Yeah. Number 24 is the one that, oh yeah, we did do this one. Is this the one you meant?
Oh no. Oh shit.
We did this one in class. Where you have to set y, look at the function and say, hey, I'm taking the limit of a function y equals f of x. So you can say f of x is equal to sine of x to the x, take ln of both sides for the purpose of bringing down the x, for the purpose of making it a denominator. Remember, multiplying is dividing by the reciprocal. Go team. Then we can go ahead and take the limit, and we end up with infinity over infinity, basically. Taking the derivative, we can then go ahead and simplify, as we did yesterday, and we end up with 0. Being 0 being the limit of the right-hand side after we take ln. And remember, 0 is equal to, well, I don't like the way they showed it. 0 is equal to, over here you would have ln of the limit as x approaches 0 of my function or of my y. So then to actually get to the limit, the original limit that I was trying to solve, we have to undo the ln, and how do we do that? E. Then e to the 0 is 1. Did we finish this one yesterday? I don't remember getting e to the 0 as 1. Okay, we did?
I think we did.
I remembered seeing sine of x to the x. I don't know what I was thinking of.
I can see.
Does that answer 24 though, my kiddos that were stuck? And we have to take the ln and bring down the power. But remember, ln of the limit, I like it that way. Ln of the limit is what we have left, is what we solve for, so we have to take e to finish off the problem. E to the power of this. Anybody still need to look at 24 a little bit longer? Okay. Brendan, I remember you had a question on number 20. Let me back up there for a second, okay?
No, I got.
Oh, it made sense? Oh, yeah, it was the weird one. Okay. Sorry, ln properties. Number 36, the final answer is 1. I'm not saying anything different. Final answer is 1. The last 2 problems I messed up on is the final answer. And I think you just were able to do 1 over u times u prime for both, right? And then just simplify. I would just simplify. And then they were able to plug in. I think they took 1 more derivative though. Yeah. They did multi-count a couple times. But guys, if you get something nasty like this one, because you had a fraction over a fraction, a complex fraction, definitely simplify first. Don't go taking derivatives with quotient rules. I understand why you might have. Because you might have plugged in, you would have gotten 0. Actually, no, you would have gotten infinity over infinity. But yeah, if you can, I mean, this is a complex fraction. They simplified it first, then life is so much easier when you go to do what we thought again.
Well, how the exponent things don't work out, like on the last question. So that's one down. So like.
Oh, because you're not going to infinity.
Okay,
If you're going to infinity, it would be 2.
So exponents only work when it's going to infinity.
degree test.
The degree test.
Yeah. Or only when you're going to infinity, or when the question asks find the horizontal asymptote, because once again it's asking you at end behavior going to. Okay, does that make sense? Go team. Okay, number 44. We had some questions on this one. It was very similar to 24, yeah? So, for the very similar problem, we're going to do a very similar procedure of taking ln of both sides. This is the one, the few that you guys asked on. So ln of both sides again. Now they're taking ln of the function, they're trying to, in a sense, manipulate the function, not manipulate, maybe transform is a better way of putting it. In order to get it into a more friendly form for L'Hopital's. And then once they get it into that more friendly form, I don't know, in my notation, I like writing the limit, that way you can actually see right here, ln of the limit is equal to the limit of this side. That way when you get all the way down to 0, you don't forget what's actually going on. Meaning that over here on the other side, you do have, in a sense, ln of the original limit as x approaches, what was it, pi over 2, from below of your function. And remember, this is what we're trying to solve for. We took ln of both sides. And taking ln, we were able to get to 0, solving the other side's limit, but we still want the original. So that's why we have to do e to both sides, resulting in a final answer of 1. So just in case we're just going with what they're doing, remember the original problem. Oops, sorry. Cosine x to the cosine x. What I would have done originally, just taken ln of one side, and then written how that is equal to ln of, well, I would have technically just brought down the cosine. This would have been my first step. Because then I'm going to go about solving this one, which is what they do over here. With ln of cosine, and then remember, multiplying by is dividing by the reciprocal, so you could divide by 1 over cosine, which they make divided by secant. Then they went ahead and solved that. They've made that eventually equal 0. And then here's where my step comes in of, okay, yeah, but that's still ln of the limit that I want to find. I need to do e to the power of in order to solve. I think this makes more sense in my head as far as organizing the work and having a reason, a rationale as to why. So if that helps you as far as setting up, I would go ahead and steal it and use it. Yeah.
So you can move, so that's a property, you can move the ln.
Taking limits of compositions of functions, yes. It's the same. It's not same, but similar logic as to why when we have, like, for instance, a square root of x over x plus 2 limit as x goes to infinity. We look inside and we take the degree. It's because we're ignoring the square root. In a sense, we're decomposing the function, taking the limit of the inside and then bringing in the square root.
So, like in your case, when you say about so square root of like x squared plus 2 over x.
Sure, we can do that one too.
Like, wait, no, that's other. Like x. And then you
can think of this as my f and this is my g. It'd be the same thing as the square root of.
And yet
which is what we do. I mean, we go looking on the inside and then we think about the square root after the fact. Similar to what we're doing with ln.
okay.
Does that kind of make sense? Yeah. And there was like whole tables of, oh my goodness. There was like a whole table of limit properties. I think we just skipped over writing down because we were lazy. And that would have had one of those properties, would have been the composition.
I don't really understand why you have to do the whole e to the ln of x thing.
Do you understand why ln is really helpful at the beginning in order to bring it in and bring down the cosine?
Yeah.
Okay. So since we had to put an ln in the beginning to be able to do anything to break apart this function, the problem is when we brought that ln in, when we solved this side, we were solving this 0 is not the original problem. Does that make sense?
Yeah.
So this side, the 0, is not the original problem. What it ends up equaling is, and we look at what we actually did, ln of the original problem. So that's why I say ln of the original problem is 0. If we want the original problem that we're supposed to find a solution to, we need to get rid of the ln. So, does that make sense? Cool. I think we have at least one more even. There's something else on the next page. 60? Ooh, 60, 64, and 66, and then we're done. So, number 60, I think we can see them all. 60A. It seems like the decimal points are getting more and more fixed, stabilizing to 0. Yeah? Letter B. Why not L'Hopital's? It's not indeterminate. Not L'Hopital's because it's not indeterminate. Number 64 is C, and then 66 is B. All right, what questions do we have? We covered most of them? You guys already figured it out and wrote it down. Now, eyes on me. I was going to come around and do a spot check. And I see quite a few of you that would have been 0s. Some that are frantically writing, some that are just being completely honest and being like, yep, I don't have it today. I did have 3 different ASB kids that were going to be gone, so technically I wouldn't check those until Tuesday anyway. But listen up, if I do a spot check starting now of all the homeworks on the days that they're due, are you going to be ready? Yes. You should start being ready. All right. I won't spot check today, but that was a warning. Right, 3 ASB kids are the ones that saved you. Saved your little hides. All right, here we go. Section 9.3.
I have a question.
Yeah.
If you ever don't do a spot check, can we still show you our homework and get extra credit? Like a half point of extra credit. Because, see, I would love
No, I think most people would just ignore me altogether with that one, which would be kind of sad. Mrs. McCray is doing something really interesting in middle school. Here, they don't.
I love Mrs. McCray. Short because our attention span is as well.
I know that's the scary part. No, literally, like our entire way of being able to communicate is better. It's pretty sad, actually. Which is why you have these things. I don't know. I got this email from you guys know Eva. Well, maybe you don't. You're not really in these circles. Like Evites. Does anybody use Evites at your age? Yeah. Okay. Evites are like the little like you can send out and be like, hey, come to my house for this book. We use it for, like in Bible studies and stuff like that, and game nights and whatnot. But like adults do. But Evite had this whole ad from Common Sense Media, which is they try to like kind of keep things cleaner, nicer, like morally higher than culture normally says. And there are all these like pre-made invites for like device-free dinners. So, like have a family dinner without your phones out. Like it's super sad. And, like, but it's like take the challenge, and it's I don't know, like it's cool in what they're trying to do, but they're doing it for a reason, and it's just sad.
It's like some people do this thing where they like everyone puts their phone
Like a box or something, right?
in the middle of the dinner table, and then whoever grabs it first has to pay for dinner.
That's a great way to do it.
Someone did that.
That's a fun idea. Like, literally, because otherwise our communication, our socialization, and even like our depth of relationships is just deteriorating quickly. Anyway, let's not bemoaning the fact. Let's maybe ponder when you hang out with friends, actually asking them about life and how they're doing, and not just laughing at the latest meme, etc., etc. No, like it's not a bad thing to do that, but how deep are you getting with someone and how they're actually doing and how much you actually care for them as a person if you're just talking about music and memes the whole time? Now, is there some place for having fun with people and relating to them on silly things? Yes. No. There's space for that. Common interests, etc. But if you never go deeper, when life starts to go downhill, who are you going to lean on? Who's going to really know you that well? Who's going to reach out to you? Anyway, something to think about. Depth of relationships and not just breadth. Life lesson. Intro. What's going on up here? I copied this whole bit of wording for a reason. What's the reason? The exponential function e to the x grows so rapidly and the logarithm function grows so slowly that they set standards by which we can judge the growth of other functions. E to the x ln of x and x suggests how rapidly and slowly e to the x ln of x respectively grow in comparison to x. X being y equals x, the normal linear function, right? So you have e to the x, which swoops up really fast. You have x that just kind of goes, up 1 over 1, up 1 over 1 forever. Then you have ln of x that goes slower. So we have the high, the middle, the low. In fact, all the functions, a to the x, exponential functions where a is greater than 1, grow faster, eventually, than any power of x, even x to the million, and hence faster than any polynomial function. To get a feeling for how rapidly the values of e to the x grow with increasing x, think of graphing the function on a large blackboard, whiteboard, whatever, with the axes scaled in centimeters. At x equals 1, e is about 3. X equals 6, e is 403. It's about to go through the ceiling if it hasn't already. At x equals 10, e is 22,000. Sadly, in our grapher, I think we've kind of minimized the effect of e in the sense of, it swoops up. But how quickly it swoops up is ridiculous. At x equals 24 inches, the 24th tick mark on the graph of e to the x is more than halfway to the million. And at 43 centimeters from the origin, the graph is high enough to reach well past the sun's closest stellar neighbor, the red dwarf star, approximately 30. Is it hard? E to the 43rd is 5.0 light years. What? Yeah, with x equals 43 centimeters from the origin, the graph is still less than 2 feet to the right of the y-axis. In contrast, the logarithmic function grows more slowly as x goes to infinity than any positive power of x, even x to the 1 over a million. Because ln and e are inverse functions, you have to go nearly 5 light years out on the x-axis to find where the graph of ln is even 43 centimeters high. Because ln, as x goes to infinity, go to infinity. Yes. But how fast? Not very quickly at all. In fact, all the functions, log base a of x for a greater than 1 grow slower eventually than any positive power of x. These comparisons of exponential polynomial logarithmic functions can be made precise by defining what it means for a function to grow faster than any other function as x approaches infinity. What are we talking about? Comparisons. What about comparisons? Relative rates of growth. And this can lead up to things like relative efficiency of sequential and binary search algorithms. Interesting. Efficiency. What makes a certain app more efficient than another one? Give an example of something that you might want an app to do to be productive to your life. Not a game, not something that's just entertainment. What's something that an app could actually help you with?
Make the right choice.
What?
Make the right choice.
I'm not sure if an app maybe, okay, so maybe like some sort of exercise fitness app, right? Okay, what if you were to go in the app store and if you were to hit search and type in fitness?
You get like so many different.
How many different ones do you do? Or do you get?
A lot.
Okay, so how do you know which one to try? If you want to find some sort of like step one. Okay, look at the rating. What?
The free one that comes up first.
Maybe the free one that comes up first. But what if there are multiple free ones?
And you look at all of the most reviews, yeah.
Okay, so look at the reviews, maybe look at the pictures to see which one looks to be user-friendly, which one has the fewer ads, etc.
Yeah.
He's in Tom Fish. But then coming back, how do you choose which one? Well, let's say you download one, you're like, okay, this one has pretty good reviews, I don't mind the screenshots of what it's going to look like, let's try it. If it lags, how long are you going to keep it for?
Not wrong.
How long? You're going to delete it and try to find another one.
Find a better one.
What makes a program better than another, or an app better than another?
Wait, what?
Not just what it does, but how quickly it goes. And what affects how quickly a program goes?
The relative rates of growth.
It's
How many steps it takes to accomplish an objective. So you want the most efficient programming, aka the programming that accomplishes the goal but in the fewest number of steps. Because the more simple the programming, the faster the program. Now, of course, there are other things to deal with speed. Some of it might be your phone, but coming back. As far as the program itself, the most efficient program, there might be 2 to 3 to 10 to 20 to 100 different programs that accomplish the exact same thing, but you want the fastest one, right? And maybe not just the fastest, but that's one of the biggest things that we appreciate. Fastest, well, accomplishing the goal in the fewest steps. Give you a couple seconds. I've never seen a relative efficient, well, not that they couldn't bring it on to AP somehow, they just had to give you a function. I haven't seen them asking you about the relative efficiency of sequential and binary search algorithms, but I still appreciate the idea and how it relates to technology in today. The efficiency. And to get us there, well, we're going to talk about relative rates of growth. And it might not be exactly what you expect because, according to what you're writing right now about growing faster and growing slower, I'm trying to help you develop more of a sense of why the degrees of certain functions are greater than others without just using things like L'Hopital's, where it's like, well, of course L'Hopital's is true, so let's go ahead and, well, L'Hopital's had to come from somewhere. To talk about more of the background, the foundation, the underpinnings of some of the things that we do and that we just assume are super simple to think through. So what you're writing down below is if f and g are positive for x being sufficiently, man, I could not say that, sufficiently large. I know, struggle. For very, very large numbers. Sufficiently large, meaning large enough to see the ultimate behavior, the ultimate end behavior of a function. If f grows faster than g, aka g grows slower, limit as x goes to infinity of top over bottom, well, if f is growing faster, g is growing slower, then all of those ratios will be increasing, hence approaching infinity. Now, yes, we know that from the degree test. Top when we go to infinity, check the sign. But we're getting into where we can apply these. Let me zoom in. I think some of you guys are having trouble reading. Is that why we're helping each other?
So which part should we write down and that should write down all of it?
Well, I would just say sufficiently large values of x. You don't really need to write x approaching infinity because you're writing it in all of your limits down below, I suppose. But you do want to identify f is growing faster and g is growing slower, which is applying the idea of the degree test, basically, is what's going on. Maybe you're trying to think about where the degree test came from. I did try to explain it to you, and some of you are like, oh yeah, it makes sense. I'm not exactly sure you could apply it. Can we keep going?
Oh.
So if you want to put off in parentheses degrees, that might be a good way of thinking about it. When we talk about degrees, what we're really talking about is the growth. And not the growth at any point in time, but the growth technically for x being sufficiently large. Man, that word. Sufficiently large. So we're not saying at infinity, we're technically saying towards infinity, so then we're pondering large values of x. I didn't ask. How about now? Ah, yes. Okay. So, let's see if this makes sense. Does it make sense? I can say the fact that if f grows faster than g, then for sufficiently large values of x, g is basically negligible. What do I mean by that? How can I just negate? How can I just ignore? How can I discount g if I have a ratio f over g? Why doesn't g matter anymore? Just because f grows faster, I just ignore g? We do it all the time. Top wins, you just ignore g and say, whatever, you don't matter, sorry. Right? Mm-hmm. Bottom wins, we totally ignore f. We totally ignore the numerator and say, whatever, you don't matter, sorry.
Mm-hmm.
Yeah, how does that work? that mean G never matters? No. Just means for larger values of x, sufficiently large with ln means sufficiently large is what, x equals 10 maybe? Maybe even 5, maybe even 2. But for other functions like, I don't know, 1,000,000 times x squared versus 1/3 x cubed, you're going to have a pretty big x in order to let the x cubed win. But eventually it will happen. When we look at degrees, we're looking at the potential of a function, for which if we allow x to get big enough, its potential will eventually outgrow the other with no turning back. And so if f is growing faster, eventually it will surpass g if it doesn't start off surpassing it right away. And it will be growing by greater and greater steps as g is growing smaller and smaller. Hence the ratio will be growing. So what we're looking at is the ratio itself. We're not focused on the individual functions, even though they give us a clue. This is just kind of like, guys, this should kind of remind you of an old math property. Remember what old math property this should remind you of? If f grows the same rate as g and g grows the same rate as h, then f grows the same rate as g. Yeah, the transitive property. That's why it's called transitivity. I know, but you guys have seen that property since like what? Pre-algebra, math, something like that. Geometry definitely, when we talked about logic a lot. But then they go ahead and show the proof as well, saying that, well, if f is growing greater than g, what we can say is the limit of f over g is a constant. No, same rate, sorry, same rate. Same rate, think degrees are tied, they're going at the same rate. So the limit would be a constant. Same rate limit is a constant. So if we try to put them together, f over h, we could just use the other two. We could say, oh, constant and a constant, therefore, oh, of course, they must be growing at the same rate as well. Because remember, at this point in math, we can't just look at it and say, oh, it makes sense, must be true. We have to have some sort of reason behind it. Anyway, I thought that was an interesting reason as to why. Using limits to actually make a proof of the transitivity of growing rates. You good? Okay, so let's do some examples. What on earth is going to show up in this homework? This is a weird section, right? It's a lot of ideas. Just giving you like a little glimpse into, oh, a statement that seems to make sense, but why? Oh, stink, I have to think of a way to show it. Okay. Number 1, show that e to the x grows faster than the given function. Of course it does. This is dumb. No, show why. Because it does. But show why.
So you just take the limit, right?
Nope, not graphing it. Not plugging in numbers, take the limit. We're applying limits to infinity. Because we can prove that e grows faster if the limit of e over my polynomial is infinity, or if the limit of the polynomial over e goes to 0. So which one do you guys want to do? Polynomial over e or e over polynomial? Okay. Exactly. It's an application of L'Hopital's. L'Hopital's can tell us who's growing faster. And like, well, this one's obvious. Well, good job, go team. But others might not be. So you do it pretty closely, just by taking quick derivatives. If you guys are cool, which I know you are, and because I'm much more lenient than I should be, couldn't we eventually get to the limit as x goes to infinity of e to the x over what? Where would I stop? 6 equals infinity. True? So therefore e goes faster.
Like, I understand why you did the limit. Why did you put, like, why did you leave it fraction?
Because back at the very beginning of our notes, check out that green box talking about the relative growths. Sorry. If I can show that the limit of f over g is infinity, I know f grows faster. Does that make sense? Okay. Show that ln grows slower than the given function. Wait, why does ln grow slower than that function? What? Well, what would we do? Make a of a, and then yeah, just choose one to go on top. Doesn't really matter, right? So you have two different properties. Kyle's already thought ahead, and he's like, well, if ln is supposed to grow slower, then this limit should be 0, because that would indicate that the bottom is growing faster and the top is growing slower. So if we plug in infinity, ln of infinity is infinity over infinity. Well, infinity minus infinity. Now I'm just confused. What do I do? L'Hopital's. You could be super snazzy if you would like, if you're kind of confused about the indeterminate forms. And you could divide everybody by ln, that'd be 1 over x over ln minus 1. You'd end up with an infinity over infinity within the expression, so yes, L'Hopital's is legal. Some of you might have thought the infinity minus infinity kind of made it illegal. Because the first derivative at the top? Mm-hmm. 1 minus 0. Good. Got it. How about number 9? Oh, this one's easy, right? After just one derivative, don't we have, 2x over 2x plus 4? X squared grows at the same rate. Should be a constant. If you go to L'Hopital's again, aren't you going to get 1?
They're the same sign.
Has to be a constant, right? It could be any constant. They're going to be growing at the same rate if the limit is any constant L.
So that could, so it was like 2, 3, 4. It's still the same.
Where's the constant is 0?
The limit, no, if the constant is 0, remember?
Yeah.
Any non-zero constant. I think that's actually stated in your table. How about these two? How do you short that? Why did I do that? Cheaters. Oh, it's so much easier to take the derivative, right? So remember, it's x to the 1/2 power, power property of logarithms, pop that in front, take the derivative at the top, and I end up with, I'm doing this because L'Hopital's is more than legal, you guys know to plug in and check it. Ooh, derivative of log base 10? Kind of Labu, but,
1 over x times ln 10.
1 over, just like we would x, but then we have the limb down there. Wouldn't that end up being the same thing as x ln of 10?
2 over 10.
Where does you put it?
All over, that's scary.
So it'll be 2 over 10.
There we go. It'd be x ln of 10 all over x. Oh, the 2 needs to go up too. Bummer. 2x? 2? I'm messing it all up. Long story short, you end up with, I know, I thought I could do it really quickly and that didn't work so well. So it's 2x ln of 10 all over 2x. What's my limit going to end up being?
1.
1 ln of 10. Remember, ln of 10 is a constant, so we're going to go one more iteration of L'Hopital's.
But why would you even need to do that? Because then you cancel out, right? X ln of 10 over, or 2x ln of 10 over 2x.
Yeah, you could reduce. That's true. You guys don't need to do another iteration of L'Hopital's. Good thing. But still, it's constants. They grow at the same rate. Show the 3 functions grow at the same rate.
So 1 to 2, 2 to 3.
Yeah, compare this one and that one.
And
And so therefore that one and we're done. So then you do 2 instead of doing, how many different rearrangements can we do? 1, 2, I guess instead of doing 3. Say just one step.
1 over 2 and then 2.
Yeah. So it could be 1 over 2 and 2 over 3, and then that would prove 1 to 3, so we'd be done. Is the transitive.
Make sure it's the same coefficient. Or the same.
Nope, doesn't have to be the same coefficient. Remember, it just has to be a limit, a constant. A constant limit. And what's interesting, the idea of growth isn't whether or not the ratio or the limit would be a constant other than 1. It's just if it's a constant at all, a non-zero constant. So here's the algorithm efficiency idea. I think it's the end. Yep. Okay. The fewer number of steps a computer must take to accomplish a task, the more efficient the algorithm. We already talked about that. The idea is between a sequential versus a binary search. A sequential versus a binary search. Sequential, you guys know what that word means, right? Sequential is you just go in order. True? Binary, cut it in half, cut it in half, cut it in half. Interesting. If you had all of Webster's dictionary, all of the words put into a computer, and then you wanted it to find a certain computer, like for instance, if you were Googling in Chrome, define, and I don't know, give me a word that might be a little difficult for someone to define. That's not helpful whatsoever. Article.
It is.
Okay, it is hard to define. A word with a better definition. Anyway, okay, fine. Define the. Chrome comes up with a definition and how much out of 10? Depends on your Wi-Fi. Let's just say.
No, don't say that. Triphobia.
No.
Why?
Okay, define the, right? Question, if you had the computer program doing a sequential search, it could go ahead and go through all the words in Webster's dictionary until it found the words that started with the letter T. And if it was sequential, it would go through all the A's and the B's and the C's and the D's and the, oh my goodness. And then once it found the T's, then it'd be like, okay, TH. It'd keep on going until it could match the TH. And then like, okay, THE, da-da-da-da-da, until it matched THE. Finally, done. Binary would say, instead of going through all the A's and the B's and the C's and the D's, it would say, okay, pick the word, in a sense, this is one way of thinking about it, pick the word in the very middle of Webster's dictionary. Okay, I have no idea what the middle word is in Webster's dictionary. What do you guys want to guess?
Mortimer.
Okay, sure. Mortimer, there's going to be a definition for that, but that's okay. Let's say mortuary. Okay, that's awful. How about mongoose? Mongoose. Mongoose. It says mort, and I was trying. Mongoose. Shush. Mongoose. Okay. Pick the word in the middle. Mongoose. Does mongoose start with a T? No. Is T going to be before or after? And they would have a little value judgment. After. Guess what? Now it only has half as many words to guess. Then it would say, what's the word in the middle of mongoose and whatever is at the very end of the Z? Yeah, sure. Zoo is leader. I don't know. Okay. So, I was going to say xylophone. That's totally wrong. Anyway. I was like, well, Z-Y would be nice, but no. Okay, so, anyway, so we have the N's and the Z's. What's it going to do? Pick somewhere halfway in between.
Yeah.
Is it a T? And that only has half as many. Guess how many steps fewer that's going to take than all the A's, all the B's, all the C's, all the D's, all the E's. Will this one eventually get there? Yes. But does this one get there in a much more efficient way? Yes.
Cody.
With the whole binary idea, coding, programming, what?
That's a lot more than the program than just type it in.
My phone's better. Sorry.
Sequential.
I'll admit.
Well, sequential, wouldn't it be much easier to program something sequential?
Yeah, but I said binary is a lot more.
Like recursive, but is it much more efficient to go binary? Yes. Here we go. Here we go. So if you were going sequentially, Webster's New International Dictionary lists about 26,000 words that begin with A. So that's if you were just going for the A's alone. So think, if you're trying to find a letter that starts with A, you'd have to go through 26,000 words, possibly, worst case scenario, to get to the very last one. If you were to go a binary search instead, it would take at most 15 steps. Cutting in half, cutting in half, cutting in half, cutting in half. So 26,000 versus 15. Well, it sounds a lot nicer if you're trying to do an efficient program. So 15. Anyway, for listed items, the binary search is at most, hold on, n over Oh, what would that be? Log base 2 of n. There we go. Log base 2 of n. Because you could rewrite that, that's an exponential function, right? So you could make it, no, it'd be 2 to the power of, big binaries are cutting in half. You could think through. There is a proof as to why that's true. But then you guys are going to go ahead and kind of, you're not going to be doing that specific process, but you're going to be using the idea of growth to possibly think about search algorithms as well. Which one's most efficient? Fewest steps? Okay, section 9.3, due on Tuesday.
Okay.